Hello, today I'll be presenting the paper on statistical inference when fixed points of belief propagation are unstable. This is based on joint work with my co-authors Sidhanth Mohanty and Prasad Raghavendra. So let's start by looking at what's the setup of a statistical inference problem. So there is a hidden signal x on n variables, and each with alphabet from 1 through q. And then we're given m observations of x, which are denoted e1 through em, and our task is to recover x given these observations. So as the number of observations m increases, this problem shows two thresholds. So when m is really small, it's information theoretically impossible to recover the signal x. And as m grow larger, it hits the first threshold called the information threshold, beyond which the problem becomes information theoretically possible but still computationally hard. And as m grows larger, there's the second computational threshold, beyond which the problem becomes computationally trackable. And the focus of this talk will be on the second threshold, the computational threshold, and we'll see some non-rigorous predictions of the threshold from statistical physics heuristics. So let's first see a couple examples of statistical inference problems to warm up. So first is the planted Q coloring. So in the planted Q coloring, the hidden signal is a random Q coloring of n vertices. And the observations are alpha n IID edges, where each edge is sampled randomly between color classes. And then the task again is to recover the hidden coloring approximately. So here the parameter is the edge density parameter alpha, and the information theoretics threshold happens at q log q, which is shown by Babst et al., and the computational threshold occurs at q squared over 2. Which is predicted by Daseli, Kazakla, Moore, and Istbolova. So, and their prediction is based on the statistical physics heuristic. Next is a less canonical example, which is called a partially revealed block model. Here, the hidden signal x is sampled by sampling a label from 0, 0, 0, 1, 1, 0, and 1, 1 for each vertex. And then the label is partially revealed, namely the first bit of every label is shown. It could be observed. And then again, the sample are alpha IID edges. And each edge, UV, is sampled with probability depending on the Hamming distance between the two endpoints U and V. And if their Hamming distance is 0, the probability will be P0, and then similarly, there will be P1 and P2. The parameters in this case are P1 alpha, P2 alpha, and P0 alpha. So the statistical physics heuristic gives the prediction shown by the diagram below. When we fix P2 alpha to be equal to 9, the blue region in this diagram are the trackable region predicted by the heuristic, and the white region are the hard region, and the white region is the hard region. So both these examples are special cases of a more general class of statistical inference problems, which we named Bayesian Csps. And for Bayesian Csps, the general model goes as follows. So first, we sample the hidden signal x from the space of all uniform. We sample the hidden signal x uniformly at random from the space of all hidden signals. And then we sample alpha n IID clauses. Here we know two things. First is that we could have clauses of different types. Here there are clauses from type 1 to type F. And second, we also note that for each type of clause, the clause could have arity other than 2. It could have any constant arity. So a clause is sampled in the following way. First, we sample the type I from the space of all possible types of clauses, and then denote the arity of I to be ki. So any tuple of ki elements are sampled to be a clause with probability depending on the hidden assignment over these ki variables. And then again, when we get these set of clauses, the task is to recover the hidden signal approximately. And the statistical physics heuristics help us to predict the computational threshold for all Bayesian CSPs. And in our paper, we give an efficient algorithm to recover the hidden signal better than random guessing in the region predicted to be easy by these heuristics. But because of time constraint, in this talk we'll be mostly focusing on explaining an intuition behind the statistical physics heuristics that's used to predict the threshold. So the first question would be, what's the optimal algorithm for recovery in the Bayesian CSP? So a natural candidate for the optimal algorithm in this case is called the belief propagation algorithm. It's often hypothesized to be theoretically optimal, and in practice, it's quite efficient and have very good performance. To the best of our knowledge, it appears that Kozakla and Stbolova are the first to use this statistical physics heuristic to predict the computational threshold for many implanted problems. And more specifically, what they do is they try to analyze the behavior of belief propagation algorithm on certain inputs. So now we quickly take a look at what is a belief propagation algorithm. So here on the left is a diagram showing an instance of a Bayesian CSP. So here the red dots indicate the variables and the square nodes indicates the clauses, and the edges indicate a containment relationship between variables and clauses. And the belief propagation algorithm estimate the marginals of the hidden signals when given the vector graph like the one on the left. And such computation is exact when the vector graph is a tree. So essentially on the tree, this algorithm boils down to a dynamic programming type of procedure where it starts from belief variables and aggregates information at each node and compute the conditional probability on the subtree and forward it to its parents, and recursively do that until we reach the root of the tree. So more precisely and generally speaking, BP is a iterative algorithm that maintains a state M at each time step, where M could be think about as a vector consisting of 2E blocks, and each block is indexed by an directed edge in this vector graph. We sometimes also call each block a message over this edge. And each block encodes a distribution over the alphabet of the hidden signal. And the state is updated as follows. The state at time step t+1 is obtained by applying the update function epsilon to the previous time step state, mt. So if we zoom in at a message over an edge from f to v1, for instance, this message at time step t+1 is obtained by applying the update function on all the incoming message to the vertex f at the previous time step, except for the message coming from v1 to f. So from all the other adjacent edges message in the previous time step. This holds true for every message in this vector, in the state vector. And as we said before, this this algorithm computes the marginal of the variables and is precise over tree vector graphs. And in fact, it's also quite effective. It also gives quite effective estimates for marginals when the vector graphs are locally tree-like. So now the question is, for what parameters of this Bayesian CSP does our BP algorithm work? So Kozakla and Zdobolova gives a heuristic to figure out this answer to this question. The heuristic starts by the following. It first initializes the initial state to a special point where each message encodes just the trivial prior distribution over the hidden signal. So for instance, for the planet Q coloring, that would be the uniform distribution on all colors. And that's the same for all the edges. Every message is just the uniform distribution. And then we start running the BP algorithm iteration. And the first question to decide is whether M0 is a fixed point, meaning like updating it will not move the state at all. If the answer is no, then actually there exists a very simple algorithm that recovers the hidden signal just by looking at the degree profile of each of the variables. And if the answer is yes, we then decide whether this fixed point is stable. And if the fixed point is not stable, then our paper gives a spectral algorithm for this recovery problem. On the other hand, if it is stable, then it's conjectured, the problem is conjectured to be hard in this regime. So let's next take a look at what's the precise definition of being stable. So consider adding a small perturbation epsilon to our initial message M0, and then doing updates to this perturbed message, to this perturbed state vector M. And look at what happens. If the message starts to move away from our starting point M0, then we say that M0 is an unstable fixed point. And on the other hand, if gradually the update moves this state back to M0, then we say this is a stable fixed point. And by the decision procedure we just talked about before, if this fixed point is unstable, then the heuristic predict the BP algorithm to succeed in this case. And on the other hand, if this fixed point is stable, then the prediction would be that BP fails in this instance. And actually, we don't really have to run the BP algorithm to figure out whether this fixed point is stable or not. What we have to do is to find what we can do alternatively is to find B, a matrix, which is a linear approximation of our update function epsilon. And then rewrite this updated state to be M0 plus B epsilon. Now if we apply this update function L times on this perturbed state, eventually we'll get something approximately equal to the initial state plus this error term B to the L times epsilon. And we know that if this term vanishes, this error term vanishes, then this fixed point would be stable. Otherwise, if it blows up, this fixed point would be unstable. So the problem really boils down to bound the spectrum of the matrix B. If the spectrum of matrix B is bounded in magnitude by 1, then when L goes to infinity, the error term BL epsilon would vanish, and in that case, the fixed point would be stable. And if, on the other hand, the spectrum is not bounded by 1, then B to the L times epsilon would blow up as L goes to infinity, and this fixed point would be unstable. Here, I want to note that although B is a matrix that's instance dependent, which depends on basically the vector graph that we get from the instance. However, across different instances in a specific Bayesian CSP model, the spectrum and the top eigenvalue bound for the matrix B concentrates pretty well. So having an unstable fixed point versus a stable fixed point is not just a property of an instance, but rather a property of a Bayesian CSP model with certain parameters. So indeed, this heuristic predicts for what parameter regime would the Bayesian CSP problem be hard, and for what parameter regime would it be computationally trackable. So here in the unstable case, we see that the matrix B have some top eigenvectors that pushes the state M0 away from the original trivial starting point. So it's natural to think that these vectors encode some information about the hidden signals underlying it. So aligned with this intuition, Kazarklar et al. Have shown a spectral algorithm for recovery based on the top eigenvector of the matrix B for the problem of community detection. So using very similar intuition here, we give an efficient spectral algorithm to recover hidden signal better than random guessing in an unstable regime predicted by this BP heuristic. And we base the spectral algorithm on the eigenvectors of a matrix AI to the L, which is very correlated with the linear approximation matrix B. Here the intuition is the following. When L is equal to 1, we have that this matrix is equal to a low-rank matrix encoding the hidden signal plus some noise matrix. And the technical challenge we overcome is to show that the contribution of the noise component becomes very small when L is really large. And in that case, we can use the top eigenvectors of AI to the L to recover the hidden signal. So in the rest of the time, I want to mention two open questions from here. The first open question is about finding rigorous evidence for the hardness regime predicted by this heuristic. We know that in this regime, BP is predicted to fail, but could we find more rigorous evidence for the hardness? For instance, can we say that low-degree polynomials or sum of square semi-definite programs fail in this regime? From a slightly different angle, can we show hardness reductions between different Bayesian CSPs in these hard regime? Or even better, could we show that the hardness of all the Bayesian CSPs can be reduced to the hardness of a single Bayesian CSP problem, just like what happens in the worst case analysis? The next open question is about optimal recovery. In the regime predicted to be computationally trackable by the heuristic, BP is hypothesized to achieve the optimal recovery rate. And in this paper, we provide an efficient algorithm that recovers the signal better than random guessing. However, it's still wide open whether we could find provably efficient algorithm that recover optimal fraction of labels. So these are the two open questions, and that will be the end of the talk. Thank you for watching.